Okay, interference. We're going to have a whole bunch of homework questions about interference. Remember, the idea here is that we use the principle of superposition. If I have two waves traveling, I add them together. I add their vertical components together. And sometimes those will add together and make it bigger. Sometimes you'll have a positive and a negative and they'll cancel out. We call those constructive and destructive interference. And that all depends on how our sources are lined up. So here I have two speakers emitting the same frequency. That's important. They're putting out sound waves that look the same, only that one's been shifted over. Our starting point has been shifted by an exact wavelength. Well, then what will happen is these will constructively interfere, and these peaks here will add together and create a bigger peak. These troughs will add together and create a bigger trough. So over here, you'll hear twice as much sound as you did here. The intensity level will be twice, not the decibel level. The intensity will be twice. What if we move by half a wavelength? So you've got one sound that maybe looks like this. So this is a wavelength from here to here, from start to finish. What if I move over and I start a new sound right here? That's half a wavelength. And I start a new one that matches the old one, but shifted over by half a wavelength. Well, now these two will completely cancel each other out. My crest and troughs match up. So these will just equal out to nothing. And we get destructive interference. So you're going to have homework questions about where do you set up your speakers to get destructive interference. And you need to algebraically figure out where to put them so that they differ by half a wavelength. Okay, beats are kind of cool. It's what you use to tune a guitar, for example. You want your beat to be 0. We're not going to do anything with it. We will do a bunch with Doppler effect. So you guys know what Doppler effect is? You're sitting at the train tracks and you hear a train coming, and right as it passes you, the pitch suddenly drops. Like you guys have all had 8th grade science. You've probably heard of the Doppler effect. Well, here is the formula we're going to use. This is the most generalized version of the formula. So L here is the listener, S is the source, V here is the speed of sound in air. We'll usually use 344 meters per second for that. VL is the speed of the listener, because the listener could be moving. VS is the speed of the source. Here's where you're going to get these wrong. You got to be careful whether to include a plus or a minus up here. So there are all these rules you can use. Here's the easiest way to do it. Let me write down this formula and draw a picture. And I'm going to write this in a more generalized version. Okay, so I've got my listener here. I've got my source here. I don't know, maybe it's a fire truck. And either one of these guys could be moving. They might both be moving in either direction. Here's my suggestion to you to get these pluses and minuses right. You draw an arrow from the listener to the source. From L toward S, listener to source. Anything that moves in that direction, that way, whichever direction that is, we use a plus sign for. Anything that moves the opposite direction, we use a negative sign for. Either one of these guys. So for example, if the fire truck is sitting still and the listener, say we're moving to the left, then up here on the top, I would use the plus sign. If the listener were moving away from the source, I would use the minus up here. Now, what if the guy is sitting still and the fire truck is moving? Then everything is the opposite. Basically, on the bottom, it happens the opposite of what you would expect. That's why a lot of times I'll do this as minus plus. If the truck is moving toward the guy, that's the positive direction from listener to source. He's moving in the opposite direction. I would want the minus. Think about this as a fraction. If you divide by a smaller number, the fraction gets bigger. So the fire truck's moving toward me, that should make the pitch go up. So I need to divide by a smaller number. So we'll use the minus on the bottom. If the truck is moving away from me, my pitch should go down. I need a bigger number on the bottom. Bigger number on the bottom makes a fraction smaller. I would use the plus. Okay, I know I threw a lot at you right there. You don't have to memorize all that. The key is draw an arrow from listener to source. Anything that moves with that arrow is a plus. Against the arrow is a minus. Okay, so here are some pictures describing exactly what I just said. So we draw an arrow from listener to source. Anything moving that direction is plus. Anything the opposite is minus. See, they go through all of them here. Okay, you can just read through all that. And then our last topic we're going to talk about today are shock waves. So we've got some great videos here that are much better than I could possibly draw here on the board. Watch these videos on sonic booms, shock waves. They have some nice, good animations that I can't possibly redraw. Again, if we were face to face, we'd just have movie time and we'd watch them. Sonic booms happen when you're moving faster than the speed of sound in air. So the waves, the plane is creating, planes make noise, right? They have engines. Those sound waves are trying to expand away from the plane, but the plane is moving so fast that the waves in front of the plane get bunched up and create this giant crack. Now, what most people don't realize about shock waves is they're not instantaneous. Meaning, if I'm here on the ground, here's me, and there's a plane, okay, that's my drawing of a plane. I can't draw with a damn. If this plane's moving faster than the speed of sound, it's creating a continuous shock wave the entire time. As it's flying, there's a shock wave that's trailing behind it in this cone. So it's moving and it's dragging the shock wave with it. It's not something that just happens and stops. It keeps happening. So it's going to pass by me. So the plane will be over here by the time that shock wave reaches me. So I'll see the plane fly overhead and go, oh, look, there's a plane. And then, I don't know, a second, 2 seconds, half a second later, hear the shock wave coming by. This angle that it makes here, this angle theta, is called our cone angle. And it's pretty easy to figure out what it is. If I draw in this right triangle here, this is where the plane was when the sound waves were coming to me. Here's sound coming at me. Here's the plane moving. In the same amount of time, this time it takes the sound to get to me is the same as the time it takes the plane to get from here to here. Notice this one's bigger because the plane's moving quicker than its own sound. So it moves further than the sound moves, and this forms a right angle here. So this distance here, this is the speed of sound times time. This is the speed of the plane times time. So this is going to confuse you also. I wish we could all get together as physicists and agree to change these symbols. Vs does not mean speed of sound. It means speed of the source. V is the speed of sound. Speed of the source, speed of the sound. And I could just do some quick trig here and say, oh, well, look, sine of theta should equal that angle right there, opposite over hypotenuse. The t's cancel, and we get v over vs. So sine of theta, the shock wave angle, is v over vs. I'm going to write this again. That's the speed of sound in air. Usually about 340 up here at this altitude. We'd probably use 340 meters per second. That's the speed of the plane, or as we say, the source. If we take the reciprocal of that, remember the plane is moving quicker than sound. So Vs over V, I flip that fraction over. We call that the Mach number. So you've heard of planes going Mach 5. That would mean their speed is 5 times bigger than the speed of sound. Okay, now interesting questions we're going to do here. We're going to find that angle. That's pretty easy. Finding the angle isn't hard. Questions that I got wrong when I took this class back in, when did I take this class? 96 maybe. We had questions on our test about finding the altitude of the plane right here. And I got that question wrong every single time because I made the mistake of thinking this time would match this time. Because I thought the plane goes overhead, the plane's right on top of me, plane moves, sound moves. These times should match up. No, that's where you'll get that question wrong. These times match up. The plane was back here, made a sound, shock wave. Plane moved this distance. This time matches this time. We set up this big triangle to find our angle. Then we set up this little triangle using that angle we just found to find this distance.